Welcome to Unified Conferencing.
Stereochemistry is on the R. Yeah. Okay. And then nitrogen is not stereochemically defined. It is, in fact, sp2 hybridized to ding dong.
Okay. Instead of like put it down on the front R.
Yes.
They're all the same.
Well.
Can you shift the camera? Actually, can you go back to like just the second half? Can you adjust the camera again? Can you adjust the camera again?
Why would otter make its food wet? I understand that, but still, you can imagine, like, if you pre-stir acetic anhydride or acetic clarification, it eventually crushes all of it. But anyway, I mean, if you fixed it, you fixed it. It doesn't matter how it would use not as hot. You're in an impurity, right? You're in an impurity, right? Oh, in this period.
Anybody need coffee? We got like 500 of these cups because we thought everybody's going to want coffee.
I'll take a souvenir cup.
You're like, that's it? All right, you can get a cup anytime. Yeah, okay. I just hope Scripps doesn't change the logo again. Someone was complaining on Twitter this morning that they didn't like that when they went to an interview, part of the interview was people asking them retrosynthetic analyses on the board. Just wondering how else do you evaluate a chemist? None of us have personal skills, so there's nothing, what's left? Can you do a retrosynthetic analysis or not? Anyway, you folks don't have to worry about that. say, TAs? Can we start a minute early?
Clock's great.
It's okay. How's it going in Florida over there?
It's good. I mean,
Good? All right.
in what context?
Metaphysically.
It's open for answer, whatever you like. Okay, so we need to finish 1,2-azoles, cover the mystical isothiazoles, a figment of human imagination brought into being. And then we're going to get into 5-6 fuse systems that are probably at the apex of confusing heterocycles. We're starting to cover in the next few classes many of those kinds of heterocycles that I promised you at the very beginning, the ones that bewilder a lot of people. But before we get into that, we need to cover these last class of 1,2-azoles, the isothiazoles. And all of this starts with the natural product colchicine. So colchicine, a very exciting natural product. There's still, I think you'll see papers today even where people are looking at this natural product, and many of the big names of organic chemistry have worked on this. Before I get into the Woodward synthesis of colchicine, it's probably worth just reminding you of the Eschimoser and Boger approaches to colchicine. Eschimoser was the first person to finish the synthesis in, I think it was 1959, which was, I think it, in his opinion, cemented himself as a sort of upcoming leader in the field of natural product chemistry, and certainly got Woodward's attention, that's for sure. Anyway, his approach starts with a heterocycle we learned about in lecture 11, I believe, the pyrone. And what he does is he takes this pyrone and he needs to add some carbons onto it, of course, to get that troponone ring system. And so what he does is he takes this and he reacts it, as you might imagine, under Diels-Alder type conditions, some heat, loss of CO2. Bless you. To give that adduct, and when you take this adduct and you treat it with boiling sodium methoxide, it turns into this, which has a name. Did you guys cover colchicine in classics class? Okay. I used to teach it. Anyway, you get that intermediate, which is known as a norcaridine. And that norcaridine then undergoes electrocyclic ring opening, giving you the 7-member ring system you see here, which is then, after many functional group manipulations, turned into the final structure. So that was the first synthesis. Dale used a similar type of strategy, but a very different approach, but used that same type of strategy at the end. The Woodward approach was quite different, and it begins in the classic Woodwardian way, and in that you've got a 7-member ring system, and back then it was the larger the ring systems got, the more frustrating it became. And coupled on top of that problem were the annoyances, as Woodward called them, of the nitrogen atom. You know, back then the sort of lore was alkaloids were a lot more difficult than terpenes because they had been obsessively studying terpenes. People like Stork said, when you put a nitrogen atom in, you add 7 years to PhD. Of course, we know that's not true today. I would argue alkaloids are probably easier to make than terpenes. Right, U0? Yeah. I think they're far easier because nitrogen have they have teeth. They can grab onto things. And you can base your whole retrosynthetic analysis upon that idiosyncratic reactivity. Anyway, back in the 60s, nitrogen was a bit of a pain. So the point of this installation of this heteroaromatic ring was that it would first shield the annoyances of the nitrogen atom, and secondly, act as a template that would allow for ring closure to take place. Now, there was a tetrahedron paper published a few years ago where they go into the lost synthesis of colchicine. And the lost synthesis of colchicine actually involves the use of a pyrrole. Unfortunately, that strategy completely failed, and it was lost. There was no literature on it until this tetrahedron paper came out, but last time we taught this class, we didn't know about it, so we couldn't teach it. Anyway, it was a pyrrole approach, but unfortunately at the end, he couldn't dismember the pyrrole to give the product. So they switched to this new compound, which he termed the isothiazole. And I think, Woodwardian prose is always fun to read, and maybe we'll just read this one paragraph from his Harvey lecture. He says, one aspect of our plan to base the synthesis of colchicine upon a simple isothiazole intermediate might well have given us pause. A forceful reminder of the fantastic multiformity of organic chemistry is provided by the fact that although literally millions of different organic molecules were known at the time our plan was laid down, no simple isothiazole of any kind had been prepared. That's pretty cool. So he thought, all right, well, let's just invent an isothiazole. It should be easier to dismantle. Okay, so retrosynthetically, we can go back to this disconnection through some simple Friedel-Crafts. We can forge this through a Wittig, which at the time was, I think, the RCM of the time. Right? He even mentioned when he used the Wittig, like, wow, this is a almost inaugural use of Wittig in organic chemistry. Right? So this dates the synthesis quite well. And then you can do a benzylic bromination, make the phosphonium salt, and it comes from that intermediate that needed to be made. Okay, so the way he made this was taking the vanillus amide and treating it with thiophosgene and triethylamine to give out the product. So we need some help on how to make this isothiazole. We still have who's on the isothiazole team? Han? I thought you were on the isothiazole team, weren't you? You can tell me anything, really. Tell me about your research you do in your lab, or I'm open, or whatever gets people excited. But yeah, if there's nothing else to talk about, let's just put this mechanism up there. Whatever you like. I'm serious. Sorry, say that again. I can't hear you.
The electron to your mean pushes the epicene to the double bond, and the electron goes into the ion bond.
Okay, that sounds good. All right, now what do? Tautomerize? Yeah, well, once I kick in, how exactly do you want me to... So you want me to move electrons here, and then I guess I'm going to have to kick out a chlorine too, and so I guess you're making me make this strange thing. Is that what you want? It looks weird, but it's certainly a possible mechanism. There's another possible mechanism which is kind of funny because it wasn't really rationalized until... So this synthesis by Woodward was completed in 1963. And as you know, in 1965 is when he published the rules for engagement in pericyclic reactions, along with Hoffman. And so you can also imagine this reaction taking place by the intermediate anion here, which is a pretty easy anion to make. And this is a 6-pi system, which should be amenable to a disrotatory thermal closure to give this type of species, which can then be quenched with solvent, and then or proton transfer, followed by loss of chloro. Hahn's mechanism is fine, essentially. You can draw the carbene if you like. The key to remember here in isothiazoles, and we're going to see this over and over again today, is that you can attack sulfur, and you need there to be some sort of oxidation state balance in order to get the isothiazole. So that brings us to the ways of making isothiazoles. Here they are. These are the two main ways. So you can generate this type of imine in C2, which can exist in this imine form, or it can exist as a vanillus thioenamide. That's fine too. So the vanillus thiamide or the imine, either one is fine. And you use an oxidant. What is the oxidant? Well, it can be I2, it can be Br2, it can be H2O2. In some cases, it can be air. The point is, you don't need DDQ. It's not a very strong oxidation required here. The other way of doing this is from these sort of Vilsmeier type intermediates. If you imagine R3 being able to equal to H. And in those cases, you'll usually add in something like thiocyanate, which will give you SCN here. And then you add an ammonia. And the ammonia will give you the imine, and then add to the sulfur and lose CN. This is it. If you can remember these two routes, it's all you need for today. That encapsulates pretty much 90% of what I've ever seen people do to make an isothiazole. There are some random crazy ways of making isothiazoles, but you don't really encounter them much, so we're going to leave them out. Questions? Okay, so let's do a couple of case studies of isothiazoles. We'll cover 3. The first one is geodon. So if you look at the front page of your handout, you see geodon there, and it can be brought into 2 distinct pieces. One of them is an oxindole, and the other one is the isothiazole. So we won't need to cover how to make that. We're fine on that. What we do need to cover is how to make that. And that turns out to be problem of the day number 1. And in problem of the day number 1, you have a orthothiobenzonitrile. And it's treated with piperidine and air, and out pops the product somehow. So I assume nobody wants to take the iPad, but hopefully someone can tell me what arrows to draw.
Do you make the amidine first? And I guess from there you oxidize sulfur.
To what?
Disulfide?
Disulfide. Nick is coming in with the assist.
Yeah. And now you just close back in.
Okay, in actuality, the first thing that happens is disulfide forms. But it's degenerate, so there's nothing wrong with this mechanism. There's some extent of this happening too, what you drew here. The point is you got your oxidation from air. Great. Can we use a similar maneuver here in this next one from Park Davis, these anti-HIV compounds? We sure can. So all we need to do here start off with that disulfide acid, do your amide bond formation, and it will spontaneously close shut to give you these isothiazolones. How about this orexin antagonist? I guess this is for sleeping disorder. Some good disconnections here. What do you say, Cheng? Any thoughts?
I think we can do the exact same thing.
What does that mean, the exact same thing?
Break the sulfur connection bond. That's what they do to
something like this would be fine. But we could use other things here too, and I'll get to that in a moment. Okay, so the way this works is they take the nitro group and they reduce it down to the aniline. Then they brominate, power selective, to give the bromine. And then they add the thionucleophile and then dump in ammonia. You could also do this transformation. Let's go through the intermediate. And this works because you have this electron withdrawing group here. So here's your intermediate. And let's just attenuate this with R. There's other ways of forging this ring system. So, for instance, another one would just be to use S8 and NH3 is another combination people have used. Another one would be to make the thiol and then treat that with NH3 and maybe H2O2. Okay, so this is a viable starting material, whether you want to add thiocyanate and then add ammonia, you want to do this strategy, this. We're going to see all these today. And the question is, well, strategically, well, it's a tactical question, which one do I use? Well, it's hard to say. It's case by case. I think the important thing is to know the three basic conditions: thiocyanate, an ammonia, or a sulfur itself, which has its own oxidant built into it, or making this. We're going to see an example in a little while of how they actually make that. We'll see that later. You can't just use, it's very rare to use H2S and a transition metal to get that directly. People use a surrogate of this and then deprotect it. We'll see that in a minute. Questions? Okay, how about this little case study here from BMCL? In there, we've got an isothiazole, and we have a somewhat strange-looking indazole. And this is a MedChem paper, so feel free to whip out your bottle of palladium. Now that I've given you permission to use palladium, do you have an intermediate you might want to start from to immediately simplify the whole puzzle? Any thoughts there, Vince? Some bonds to disconnect?
Cut off the arrow group.
Okay, we're going to get rid of that bond. Any other bonds you want to get rid of?
The other arrow group.
All right, let's get rid of both those bonds. All right, Vince. Now, extra question for you. Now that we have this compound in hand, how are you going to get selective coupling? Like, if I do this coupling, am I going to get a one-to-one mixture? Stille, Suzuki, Negishi, whatever?
It would depend on the reactivity of ions, but
It sure does, but you've taken lecture 1. So you can therefore tell us which is the more reactive and which is the less reactive.
I think the one adjacent to the nitrogen is more reactive.
Great, because?
Because it's more electron withdrawn.
Yeah, it's pyridine-like.
Yeah.
Perfect. Great. So you'll do a coupling first here, and then you'll go do a coupling there next. All right, now how do we make that thiazole? We actually made it. You can't buy it. At least back then you couldn't, 2013. Well, let me just take you through the logic of when you see a system like this. The first thing we're going to do is let's get rid of the amide to make it a little bit easier for you. Okay, now we just have that. And when you look at this, obviously there's going to be a desire to break the NS bond. Right? Let's break the NS bond. Now, now, how do you suspect we make an iminoyl bromide? Aha! Hannah says from the nitrile. So if you take this compound, I'm not going to tell you what R is yet, treat it with bromine, it goes all the way to the compound here with the R. Now, what is that R? The R is borrowing from Woodward's strategy. The R is methyl ketone. That facilitates the closure. So, this gives the methyl ketone. To get the bromine from the methyl ketone, they use a bromoform Hunziker reaction. So to go from R into Br, you use sodium hydroxide and Br2 and heat. And it cleanly goes from methyl ketone to carboxylic acid to Hunziker to bromo in one pot in about 80% yield. Pretty good, huh? All right, now we just have to make this indazole. Tucker, how do we make the indazole?
Boric acid from the bromo.
Let's just do that first. Get rid of that. Make our life a little easier. And we are in medchem mode.
And alkylate.
That looks like a problem of the day. Long, long ago, yesterday.
All right. It's the methyl layer.
That one's fine. Or you may say, hey, Phil, I really like SNAR reactions. All right. Also okay. Questions? No, you guys are absorbing this like the most powerful sponge on the planet. Awesome. Apixaban. Multi-billion-dollar drug. It might end up being in the top 3 or 4 best-selling small molecules ever. I think the last estimate is like 8 billion or something for this year. They think it'll go over 10 next year. It's used by cardiologists as a great alternative to Coumadin. Probably you know people, and you might know people in your family. My brother's a cardiologist. He prescribes this stuff all the time. It's a great drug. Saved a lot of lives. And the cool thing about this molecule, it's sort of what all of you who are aspiring to go into pharma dream of doing. So the backstory of this is that a lot of beautiful chemistry was developed. For instance, one of the people who worked on this project, one of the inventors of this, was Patrick Lamb of the famous Chan-Lamb reaction. And indeed, they used Chan-Lamb to make 1 trillion billion analogs in this series. So a lot of beautiful chemistry came out of this, and a lot of patients are currently being helped with this. So it doesn't get any better than this. This is the dream. All right, how do we make it? First thing we can do is just, let's not worry about that. Let's just disconnect that. Or you can just think of it as NAR for now. Just don't worry about that. What I want you to think about is this ring system. Don't worry about the spinach. Just talk about AR there. What do you say there, Steve? You got any thoughts on, I mean, there's no wrong answer. You want to make AB first or BA? Whatever you want. I'll do whatever you want.
Break ring.
So if we break ring B, that gets us to a system like I assume this is what you're looking for,
Yeah, something like that.
but there's another way to do it too. If you had to summarize the ways of making pyrazoles, when you look at a pyrazole from now on, I want you to think of three things that pop into your head based upon what we talked about yesterday. Bless you. You're going to think about, number one, making it through a dipolar cycloaddition. Number two, you're going to think about a cyclocondensation from a dicarbonyl. And number three, you're going to think about hydrazone logic, stitching the ring together with hydrozones. That's it. It's really that simple. Dipolar encompasses everything, from syndenones to nitrilamines, whatever you want. 1,3-dicarbonyls can be hidden inside of a heterocycle. Bless you. And hydrozones, as we'll see in a moment, can be used in a way to stitch together in a convergent fashion. Those are the three things to think about when you think of a pyrazole, folks. That's it. There's nothing more. All right, so that disconnection is interesting, Steve, but if we take your exact same disconnection, but make it a little bit more convergent, that is, do something like this, we get back to the true approach to Eliquis. Okay, the regiochemistry is perfect. The nitrilamine, where does the nitrilamine come from? Well, Steve taught us how to make those yesterday, you may recall. That little simple compound is not just a condensation to make that. It's actually via through what name reaction, Dongmin? That's a chloro on that carbon, along with an acetyl group and an ester, reacting with a diazonium salt and base. Lecture number 5 or 6. You got it. Jap Klingman. A very bizarre use of it here, but highly effective to directly make the hydrazone. Continued treatment with a little bit of base gives you the nitrilamine. Dumping in this derivative gives you the product after a monolysis of the ester. How do you like that? Pretty good. And Steve got it just by saying, I want to go and make B from A. What if we go the opposite way? Is it viable? Solid doesn't like it. Well, let's draw it out.
It just doesn't reduce complexity very much, right? Because you still ended up with a tetrasubstituted pyrazole.
Well, let's draw it out.
That doesn't really look any simpler to me than
Yeah. What's the other problem with it? What's that?
In a regioselective way, it's very difficult.
You could make it in a regioselective way. Well, there is no regioselectivity yet, but there is. You're talking about the ring closure. Ring closure, that's going to be a problem. I don't know how you make that regioselectively. That's a real problem there. Making that pyrazole is doable. But yeah, can't close it very well. So that's it. You make that disconnection, you realize, I haven't reduced complexity. I've introduced additional complexity of how to deal with regiochemistry. Whereas the top one, pretty straightforward. Okay, questions? Well, using what we just said, we have 3 strategies. That's all we have to make pyrazoles. Let's take a look at this next problem of the day, where the problem is asking you, give me 3 different routes.
I think 1,3-dicarbonyl logic is the right one for this.
All right, so Saul says, let's go with 1,3-dicarbonyl logic, which I assume means he wants us to do something
I'm
like...
just saying, like an aeroketone.
Yes?
Yeah, you lost nitrogen.
What's that?
You lost a nitrogen in your azotane.
How would you make that regioselectively?
Is it non-symmetric?
No.
Well, wait. Before we rain
I'm
on
just curious.
before we rain on his parade here.
Use a beta halo, you should get the right.
Well, hold on. Before we do that, let's imagine we've got a route to that compound. How do you regioselectively control where?
So you can go via the aryloxine. Sorry, the azopane oxine. Hydrazone. Oxine, I mean hydrazone.
And base. Is that what you're saying?
That's not what I was saying, but that.
Oh, you want hydrazone? Is that? I thought you said oxine.
Yeah, I did, but I meant hydrazone. Or that can already be IPR, and then you can just let air oxide.
But if that's IPR already, then yeah, okay. Okay, that's reasonable. If you also want to use 1,3-dicarbonyl logic and you want to make analogs, you might also consider going through that. Make the triflate or POCl3 it, followed by Suzuki coupling. And this one comes from that. And, I keep losing my nitrogen, sorry. But you guys know where they are. And that just comes from that. You can use a courteous Bouchard type ring expansion. Gets that. Then treat that with isopropyl hydrazine. Will give you the right regiochemistry because it condenses on the ketone first and makes the amide. And now you've got your pyrazolone, which you treat with POCl3, and Suzuki, your way to victory. Or what Saul suggested up above is just fine. This one, not quite perfect because you have regiochemical problems. Nobody said 1,3 dipolar.
Do I just say no?
Okay, so Max said something more specific than 1,3 dipolar. So if you use the sidnone, that's your sidnone, and that's your olefin. Problem with the sidnones and olefins, they're not really that matched. So dipolar cycloadditions work really well with electron-rich and electron-poor. They're this schizophrenic heterocyclic reactions because they either like it really hot or really cold, but they're not interested in just sort of very calm olefins, like a regular olefin like that. So the sidnone approach, not ideal. There's another approach.
Take enamine, not alkene, but the heat alkyne. Enamine of that.
Yeah. Okay. So maybe that would fix it, perhaps. That may work. The other approach you can think about is see the 7-member ring and you say, wait a minute, that's a reductive amination. Hannah's like, no way, no it's not. Yes it is. So here's what they did. They broke right here to give you and you treat that with base, and it just reacts, right? No, not quite. There's a few things we need here, don't we? Lesson. We need some activating group. Now you treat that with base.
What is that group?
Nitro. Oxidation state is built in with the nitro. Lose HNO2. Deprotect. Reductive amination. That's the way they did it on scale up. I know you don't like it, but they don't want to do the ring expansion to make that cyclo as a heptanone. These two building blocks are super easy to get your hands on. Why is this super easy to get your hands on? Well, this is just a nitro compound and a Henry reaction onto benzaldehyde. That's why they like it. So all the reactions are dump and stir. And no heat, really. You don't need any high temperature to do any of this stuff. You don't have any regiochemical problems. It's all controlled. So these folks knew what they were doing. Now, before we go on to this kinase inhibitor, I think it's valuable to just remind you that there is a section of the book, perhaps start by reminding you there's a book. So there's a chapter here on 5,6 fused arenes that we spent countless hours putting together. Basically summarizing everything, the tips you need to know when you've got a 5,6 fused ring system. How do you disconnect one versus the other? And so there's 3 guidelines that help us a lot. Help me, at least. I mean, I'm simple-minded, so this helps me. So if the fused system has more heteroatoms on one of the rings, The one with more heteroatoms, probably disconnect that one first, retrosynthetically. Next rule is if you have a 6-5, usually it might make sense for you to disconnect the 5 first before the 6. And then finally, if you have a fused system with one ring with two contiguous and one with two non-contiguous, pick the one with contiguous, because that usually comes from hydroxylamine or from hydrazine, right? And also there's the aromaticity principle. So you probably want to disconnect heteroaromes first that are less aromatic. And so these 3 rules can be applied to dozens and dozens of different ring systems. And I think and it's right almost always. Almost always right. In some cases, there's, as we'll see today, there are cases where both are right. You can go either way, and they're retrosynthetically kind of equal. So it might be useful as a way to practice for an interview or study for an exam to go through this chapter and rationalize yourself, cover the answers, and rationalize which one might be the best way to make these various ring systems. And these guidelines are all you need to do it. It's fairly simple. So that's our prelude to this next portion. So the rest of the lecture is basically going to be that. And so if you use those principles and combine it with everything we learned before in the past 14 lectures, you're going to do well. Let's talk about this kinase inhibitor. Now we've got a pyridine connected to a isothiazole.
It's more or less identical to problem to number 1. Start from the mercaptan nitro.
And instead of AR there, Saul, you mind if I put bromine? Because I want to diversify.
Sounds great.
Is that okay? All right, great. Now, I need to make that, and I promised you before I would tell you a good way to make that. Recommended conditions for this transformation?
To close the ring.
Yeah, tell me how to close the ring. You got a lot of options over here.
Iodine amine.
Okay, so what they did was they added ammonia first to get the amidine, and then they added their oxidant. In this case, they use H2O2, but any oxidant you want is fine. You can just put that on a test, it's fine. Okay, now we need to make this. And then we need to go back to lecture number 10 or 9. Guarashi-Thorpe is what you're saying? Yeah. So Guarashi-Thorpe. Treat that with bromine, POCl3. Got that. Add in your mercapto reagent. Then treat that with methoxide or DBU. Works fine. And you don't isolate this. That intermediate is directly treated with your ammonia followed by some oxidant. Then you get out the product. Pretty good. Problem of the day number 3 is a medchem versus process cage match. So you need to put yourself in the driver's seat of a medchem program directed around these fused systems. So we've got a pyrazine connected to a pyrazole. What do you say, Max, too? You want to take problem of the day number 3?
So disconnect the pyrazole.
So were you doing medchem or are you doing process?
I guess this would be more amenable to process because I want to be able to.
Okay, let me label the ring. Let's take it a little bit slow. But before I disconnect A, do you want to tell me something about the substituents from a medchem standpoint? I've got some sort of diversity going on here. I've got some diversity going on here.
Yeah, you might be able to get just O ventilation from the pyridone or do SNAR onto the pyridone.
So if we do SNAR, what would you suggest we have here?
It would be fluoro, or yeah.
Fluoro sounds good.
Yeah.
Easier than fluoro. And then what do you want to put here?
There, I think cross-coupling.
Cross-coupling, okay. So maybe we'll put an iodine there. But it could be bromine. It's fine. So I tricked you into giving me the medchem intermediate. All right, that's my medchem intermediate.
Okay, so Sandmeyer to get the iodine. And then
So Max suggests we use Sandmeyer.
or actually, that's probably the most electron-rich position. Just iodine.
So either one is fine, right?
I prefer just direct iodination.
Okay, but it's good you said that because we can do both. It's fine. I agree with you. Let's do direct halogenation. Okay, so that gives us R equal to H.
Yeah.
Now we're again in the situation of having pyrazole connected to pyrazine. And you suggested what?
To make the pyrazole.
So we're going to go from B and annulate onto their A. And just drawing, pretty much translating exactly what you said into words, into paper. That's what I get. Is that right?
So would the hydrogen condense onto the aldehyde before it goes SNAR?
Very quickly. Super reactive aldehyde, too. Not only is it a normal aldehyde, but gee, it's connected right to this very electron withdrawn ring system, and it's at the pyridine-like position. So this aldehyde is raring to react. And how do we make that thing? From even something simpler? What's the first thing you want to disconnect? Back to lecture number 3. Do we disconnect the chloros?
I would disconnect the aldehyde.
Yeah. Treat it with like lithium TMP, for instance, and then DMF. Is it wrong to disconnect B and build it from A? Is that wrong? Saul says it's wrong. Definitively wrong, he says. Well, let's think about it. Convince me it's wrong, Saul.
So,
Let's draw what would result if we did that. The move you say is so wrong. We would need that kind of starting material. Correct? And we would need to
you
annulate.
need oxidation somehow.
You need oxidation somehow.
For position.
It's true. So if you were to do that, the maneuver that would let you do it, and you may cringe. I know you're going to cringe. that's what you would get, which after decarboxylation and POCl3 gives you the product. So it's doable. It's a known prep. You may not like it. I don't either. But it's known. Why do they do that? Well, sometimes those kind of processes may be easier to scale up, or they may have the amino pyrazole just hanging around. What do you say there, Nick?
When the nitros attack the amine, also to make diaz.
They're using HNO2, and they're not getting diazotization. They're just getting nitrosylation under those conditions. Yep. Because it's a pretty electron-rich aromatic. Okay, now we got to go to process chemistry. So, Max, we're not done with you. Sorry.
Okay.
Now, with everything you've seen so far, maybe the answer's already up there.
Don't know what you mean by that. But
Well, do you think process chemists are going to want to go from that iodide and do Suzuki's all day?
probably not. So just the ketone, the diuretic ketone.
And we know how to make this already, right?
Or just, lithiate on that, onto the acetic chloride of the zinc.
There's nothing to oxidize. Just you could lithium TMP, quench it with the aryl,
Wine wrappers.
either the wine reb or the acid chloride. Now, full disclosure, if you go to this paper, it's a brazenly honest depiction of real-world process chemistry. So they mention in the paper they would have loved to do this process approach. They admit it's a better way to go. But they had a little thing called timelines. And so because of the extreme time pressure, they actually had to develop a scalable Negishi approach to deliver the tox batch. So they just took the medchem approach, and they found really cool Negishi conditions to get it to go. So they essentially used the medchem route for this intermediate batch. This happens all the time. Doesn't mean they're bad process chemists. They actually said in the paper, that would be better than to have time. But if you had time, that would definitely be the better process way to go. Questions?
They used on large scale?
I don't think it was enormous scale. Maybe just kilogram. Not hecta, not crazy metric ton or anything like that. I think it was just a tox batch, which is why the timeline was so short. Okay, how about this next one? This kinesin spindle inhibitor, whatever that is. And I believe I'm missing a group down here. If you go to the front page of the handout, you'll see the entire... I think I was missing a carbon. Where is the spindle inhibitor? There we go. Yeah, I was missing a carbon here. All right. That's a tricky one. First thing we should probably do is make our lives easy. And this is what you should do when you are faced with a problem like this. First, get rid of the spinach you can get rid of. Just like we did over here, we got rid of this stuff right away to get to the core. Let's get rid of this annoying stuff here. With the realization that this position is very ketone-like. And so it should be possible to take that and treat that with bromine, and it will alpha brominate just like a ketone. And then you can do an SN2 and build up this whole portion here. This will be protected, that will add in, and then you'll isolate, deprotect. Hannah, what do you don't like it?
Is it chemoselective on the method?
That's a great question. Yeah, it is.
Why?
Well, another good question. It's probably, it's the kind of thing that
Empirical.
you could imagine it's just because your pKa is lowered by having a more electron deficient pyrimidinone ring system than the isothiazole. That's how you would back rationalize it.
Do you have a sense of what the pKa of the ketone would be?
I'm going to say it's probably ketone territory, so we're looking probably. I wouldn't be surprised if it's around 220, 120.
If you assume that the other one is pyridine-like, though, that should be very similar.
It's going to be similar, and the other thing to consider would be that under the slightly acidic conditions, I think there's HBr in there as well. Under those slightly acidic conditions, there's much more of a driving force for tautomerization to the enamine-like form than there is for this one. It's harder to protonate that one. So I think that's probably, you're getting some enamine-like character here under the weakly acidic conditions. But that is a great question. In any event, now that we've simplified the problem, we don't have to worry about that substitution anymore. And you know what? Let's just remove this guy as well. We can just treat that with some base and a benzyl bromide. Now we end up with something a little bit more simple. Let's us just focus on the ring system and not have to worry about spinach here and spinach there. Tough call. The guidelines suggest that we might want to go one way, and Saul, you don't like the guidelines.
I normally like the guidelines. I think this is an exception where we should break B first.
Let's see why Saul says no to what the guidelines suggest might be a better way to do this. Is that the precursor we would use?
That's not the precursor I like.
Oh, I know you don't like that.
I don't think that's greatly simplifying.
All right, let's do yours. You like that one better?
I do, because now we're very close to a malonate. Or malononitrile, I guess.
There you have it. Saul has identified malononitrile. All the way back from that, somehow he saw malononitrile. Hopefully some of you did as well. What is the problem with the other disconnection? Let's take it further so that you fully understand it. In theory, you could say to me, hey, Phil, why don't you just do the 3+3 approach that we learned in pyrimidinone synthesis? What's the problem with that? Tricarbonyl, that's not so stable, number one. Oh, maybe you can make.
Buy that.
Okay. Now we purchased it. Now what, Hannah?
Do the thing.
Do the thing. All right, so we do the thing. Any objections to the thing?
Ketones are probably rebelling.
I mean,
Correct.
You can protect the ketone.
You could protect it how?
Either as some sort of alkylated species or as an acetal.
Certainly fine. I think that if you let's say put CH2 there, and then at the end you did some benzoylic oxidation, you then have to find a way to oxidize here and not here.
Yeah, I don't think that's the way.
Okay. So which way? Like OTBS?
That would be fine.
OTBS would not be fine because you would get immediate beta elimination. Immediate.
I'm saying that it's in the ketone oxidation state,
Okay.
but it's got some sort of alkyl group on it.
Still the same, like
You won't get
retroalcohol.
beta elimination? No, you won't.
Silyl ether.
Yeah, that's the
Well, but
same kind of thing.
Silyl ether where? Oh, here. Silyl ether. That won't add in one. Okay. If you can posit something like that and it's coherent like that,
We can do condensation of malonate first, and then until acetyl group.
and okay, that's another idea. So instead of going with this, just do straight malonate, and then just acetylate here, Friedel-Crafts style. The other issue is you're going to do PLCl3 in this thing, and it's going to be hard to actually stop it here and not go all the way to the dichloro.
It's a non-stop dichloro, then condensation, then hydrolysis of one chloro.
And then yep, so that's fine too. So I really think that a case like this is one where you would go armed in SciFinder to look for that. You'd find it's 100,000 hits. And then you would go and look for species like that or the dichloro, rather than trying to SciFinder something like that in the real world. So the point is you need these two disconnections because you can't say it's really context dependent. I like the top one better, but it's because I know that's what they did, and I'm biased. Right? I'm biased. Questions? Maybe we should put this board over there so the people over there can see what's going on. How about a Brutinib? The front page of the handout is a Brutinib. You can look on your sheet there. It's a very interesting covalent drug, one of the first out there with an acrylate on it that convinced people that, you can actually use these types of species and they're not toxic and they actually can cure cancer in some cases. Okay, so let's talk about medchem versus process. We've got two ring systems. We've obviously got some spinach. So let's talk about the medchem route first and delete all the spinach. Steve, what results after I delete all the spinach? Which?
Off that R group.
Get rid of this, maybe Mitsunobu.
Yep. And then the arrow group, probably cross couple.
And this thing can probably come from the same thing we did with Max over there. Which way do you want to go?
Chloro and methyl.
So you want to make A. Let's see. And then turn that into a indazole or pyrazole. Is there another viable disconnection? Same building B onto A? Same as what we did over there. You don't like this, you might like SNAR. And Steve, you're the ideal person to tell us how to make that. Vilsmeier sounds good. And that just comes from formamidine and dimethylmalonate. And then you treat that with POCl3 DMF, you get that. And then you treat that with hydrazine, and then ammonia, out pops that. I'm not sure if this, you can treat that with sodium nitrate and get the same type of closure. Conceivably, I just have never seen it on a diamino methyl like that. I mean, but that would be something you would look for. But I think once you found that you could get, this is commercial and this is free, so if you couldn't even get this, you could just mix this up with PLCL3 DMF, you get that really quick, add in the hydrazine, and you're good to go. What about the other way? Is the other way viable, or is it silly? If we disconnect here, what do we get? This carbon is an immediate signaling element for what Zeng?
Nitrile.
Okay, so let's just draw a nitrile. And this carbon is a signaling element for what Zeng?
Nitrile.
Which one do you like better? Who likes the top one best? Who likes the bottom one best? More people like the bottom one. They're both equivalent, guys. If you look in literature, you find 50% of the people do the top, 50% of people do the bottom. Some papers have both listed as they made it through both ways. Okay, we're done with medchem. How about process? Process you have to consider now. You've got the R group here. Let's think about that R group we've got. And we've got the AR there. And we would not like to use cross-coupling if we can avoid it.
Start with the diaryl ketone SNAR approach will give you the right regiochemistry on the R group. It also makes your CC bond for you.
Pretty good. And this can be made either from metallation or from, preferably from the aldehyde you've already got. It's by way of aryl metal addition, oxidation. And then add your hydrazine in. Questions?
How do they set that stereotype? Is it a single enantiomer?
It is a single enantiomer, and they have a whole discussion of that. It's, in that particular case, a diastereoselective, I think, reductive amination followed by hydrazine formation. But they also do a diastereoselective reduction to the alcohol, and then Mitsunobu is another way.
You're saying enantioselective?
Well, no, diastereoselective, because other stereocenters in the, as I recall.
There's only one stereocenter.
Oh, and that one. Yes, that one is they do, I think, a transfer hydrogenation way of getting it. Or yeah, there's a ton of patents on the way they manufacture. So even in the OPRD paper, they present like 5 different routes. They're not really sure which one is used on commercial scale.
Actually,
TAs have something to add here?
There's dozens of companies that have published different patents on how to make this like immediately after the FDA.
Yeah. Yeah, so there's probably a ton of ways. I mean, I'm sure enzymatic, biocatalytic. There's a ton of ways of making that kind of chiral amine. And that's sort of a game that a lot of generic companies play. Is the minute a compound looks like it might be approved, they're already filing patents on alternative routes. Okay, that gets us to problem of the day number 4, doing great on time. We need to make these 2 scaffolds straight out of the medchem literature, and you want to start from the same starting material. So luckily Sarah will tell us the answer to problem of the day number 4.
You go from the
That sounds pretty good. Now, Sarah, what are the conditions you would use for the pyrazole? And what are the conditions you would use for the isothiazole? Brilliant. Done. Lightning speed. How about this pan-pin inhibitor? Medchem approach. So we can Suzuki all day. What's that? Suzuki. Which one do you want to do there, Tucker? We've got one here. We've got one there.
Why not both?
We can do both. And so why don't we do this one retrosynthetically? We'll do it at the beginning, and this one we'll do at the very end. And that will get us to an intermediate that looks like this. I'll just put pyrazine for short. And they use a stili. Now, Tucker, since you're already right at the front here, maybe you can tell us a good way to put this thing together.
So you mean like leaving the NS bond?
And what do I do to close it?
HO2.
Any oxidant? So this kind of thing comes from all right, so we begin with stili to put in our pyrazine. And then we add in a thiol. And then we close it, we triflate it, and we do our last stili. And this can be brought back to a simple dihalo pyridine. Because you can metallate here and then trap. Super. How about this c-Kit PD-GFR alpha dual inhibitor? Because we all know what that means.
Can you take it back to a trifluoromethylketone?
Take it back to a trifluoromethylketone, he says. Yes?
Yeah.
And then how do you make that thing?
Well, I wasn't thinking of having the chloro there, but I was thinking of
If you didn't have the chloro there, what were you going to do?
well, an oxide or something.
Oh.
But I was thinking of like cross-coupling the L group and then just treating the hydrazine afterwards. Or that.
Is that not what you wanted?
Well, no, yeah, sure.
I mean, this is up to you, Max. That's what you wanted?
Yeah, just minus the orthochloro, but I guess it's fine either way.
Oh, yeah, you don't even need that, right? Okay, because you're going to put it in through the N oxide. Okay. It's totally reasonable. So, Max took the approach of breaking this up, looking at the pure. He basically took the guidelines, said, we're going to make or buy the 6-member ring and annulate on the 5-member ring. Perfectly fine. But the rules were made to be broken. So the other way to break this system up is to imagine that everything arose from a system like this. Via decarboxylation, POCl3, and then removing the chloro. And then you may say, hey, Phil, I just don't like this, but what if I tell you all you need to do to get this reaction to go is take Meldrum's acid, aldehyde, and the aminopyrazole. What is that reaction? We learned it in lecture 9, I think. Do you remember? Hansch. Yes. It's the same thing, right? I mean, that's Hansch condensation. And then after that, decarboxylate, POCl3, you get your product. This thing comes from, hey Zeng, what's this carbon?
Nitrile.
Okay. How do you like that? It's pretty good. Which one's better? It's up to you. But you have to know both. And look at that, we still have time. And it says if time permits. So looks like time is permitting. Now we have a pyrazole connected to a pyridazine connected to a thiophene. There are infinite ways of torturing you with heterocycles. B looks nice. I agree, Vince. Now, there's a couple of ways of thinking about disconnecting B. Let's go through it bond by bond. So, clearly, these two are going to be stationary. We're not going to want to break those, right?
Right.
If we break this one, it would require we have some sort of stable diazine that we do a sort of dehydrogenative coupling. Maybe, but very weird. I don't know how you make that unsymmetrical diazine so well. Then we have this disconnection, which would need a diazonium on that side, and then this needs to attack it. Or we have this disconnection, which has a diazonium on that side, and the thiophene attacks it. Any preferences?
I was just thinking you could disconnect both those bonds with chloro and treat with, or to the chloride, like the dichloride, and treat with hydrazine. Some oxidant.
I'm glad you said that. And treat with hydrazine and pray. And hope there's some air around too, I guess. Why you don't like it so much, Saul? You're cringing. Why?
On one side, you're trying to do SNAR on a thiophene, which is scary, and on the other side, you're trying to do SNAR ortho to a pearl type nitrogen, which is also scary.
Well, it's not so scary if you think about the tautomeric form of this. So often in the literature, you'll see pyrazoles that do SNAR, and they've drawn it like that. So don't let that confuse you. Remember, pyrazoles have both tautomeric forms. It can be this one, or I can easily draw it in that form too. So you can, in fact, do an SNAR with a system like that. High heat and a lot of prayer, and you probably need an R group here as well, because if it deprotonates here, it's also game over. So that's why we don't like that disconnection so much.
What about starting from 2-aminopyrazole and just oxidizing to diazonium?
So that's the sort of two options were diazonium on the thiophene or diazonium on the pyrazole, and Saul chooses that one. Yeah, and that sounds good because it's super easy to make. This compound. Bromination of pyrazole, Suzuki, Stille, whatever you want. Then sodium nitrate, HCl, gets the diazonium. And then it's like a von Richter, phenylene synthesis. Remember the von Richter? Nobody remembers it. Okay, but you learned it. And in the final 5 minutes, this is a great one. We've got a aminopyrimidine, and we've got two pyrazoles linked together. And everything we've learned so far, this should be like a few microseconds in terms of which disconnection you might want to make. Max, you already have it?
Well, maybe halfway. I think intuitively I feel like I want to take it back to dichloro-pyrimidine.
And then what do you want to do? Take us through the bond connections.
Well, I'd like to have the ketone there, yeah. So I guess the acyl chloride or the ester of the azole. Yeah, it's fine. And then from there, just hydrazine or an ethyl hydrazine. And then ammonia or something.
We can do that, and we can do what we did before if you want. Also,
You adjust the camera.
viable. Also fine. Where AR metal comes in, oxidize, and then hydrazine comes in. And you get 5 minutes back. And, we have one lecture tomorrow. It's a super exciting lecture on purines. And then don't forget, in the afternoon, we have a special guest speaker, Mike Sophia. So see you all tomorrow morning.
My welcome gifts to Scripps from Ruben Martinez was a book of the Harvey lectures.
Oh, so you
Woodward
have that.
gave that.
Wow.
Yeah, so I have one of the original copies.
Wow.
Is user there?
Oh no,
Or
I
a TA?
wish.
Wow. It's a great read.
Yeah, it's really interesting.
What's up?
Will the lecture or seminar tomorrow be broadcast?
I think so.
Okay, can you email me the room, time?
Yeah.
Okay, thanks.
that's someone my friend that I don't really care like more than that. We get there in that minute. We have to park. Yeah, so that will take time. I have to walk. I guess this small years won't fail then.
Was it the 10:40? We parked up front, yeah.
Yeah,
I want to continue to have this luxury. Okay. Yeah, 10:40.
10:40 you said? Yeah, cool. Wait.
Oh!
Wow, what's a baby? Remember what he said about? He mentioned we have to write a letter for future TA.
Yeah, I wasn't really sure what he meant by that.
No, he basically want a Word document that accumulates the stuff we have to fix in future.
But it doesn't make any sense to me because they're just going to go off what we already did.
Yeah, so we can just fix it now, but because we are lazy, we don't need to do that, I guess.
Like, I don't go into, like, the 2015 stuff unless I have to, right? Because I assume that the stuff that was done in 2017 was an improvement upon 2015. You know what I mean?
Yeah, but I guess what we want is some slight modification of our handouts. And I wonder, because we always email Ian or Ruben, like, hey, what is this?
Yeah.
Give me us this. So I guess we want to save that trouble. Actually, I feel much better like finishing up both problems at the project yesterday.
Yeah.
Yeah,
all we have to do is make a test now.
Yeah, make a test. I mean, we have Microsoft thing today, tomorrow, day after tomorrow, but I think it could be even worse without those stuff done.
Okay, now
Basically, when I had helpies.
What?
I got helpies before, right?
Yeah.
Like a month ago. And I got a bill from Aetna. It's not quite a bill, but like explaining what actually costs how much.
Yeah.
And I went to two emergency room twice, and guess how much it was in total?
It's like $12,000 or something.
Actually, close. 10,000.
Yeah.
Oh, sorry, not 10,000, 1,000.
Oh.
Wait. 10,000. Sorry, 10,000.
Yeah.
Wait. 10,000?
Because they probably took to get like blood work.
Yeah.
Yeah, dude, the lab fees are like to do your blood work.
Yeah.
The lab fees are technically like $5,000.
Yeah, I don't understand.
And then did they give you like when you went in, were you like super dehydrated? Did they give you like saline, like an IV bag?
Yeah. I got 2 IVs.
Yeah.
So that cost so much.
And did they do EKG?
What is EKG?
They probably didn't. The thing where they look at the ads up on you and
Oh,
push
yeah,
your
yeah.
heart?
Yeah.
Oh yeah,
They did
that's
like
like another $3,000.
Yeah, and I got, what was that? CT scans as well?
CT?
Yeah.
Oh damn. Yeah, it's crazy.
Yeah, CT is crazy expensive. Did you actually hold it? We did it for people. Oh shit.
Oh, that charger, yeah. Is this Kiri's?